Hello everyone. Today I want to teach you number theory. And I want to start with the first chapter, which is basic knowledge of number theory. Number theory. What is number theory exactly? I think is the study of properties of integers and counting numbers. Okay? And Carl Friedrich Gauss said mathematics is the queen of science and number theory is the queen of mathematics. Okay, this is one of the most famous quote from mathematicians, especially in number theory. Number theorists, what do they study? They study prime numbers and mathematical structure formed by integers such as rational numbers. And in this chapter, there will be two topics, and I will divide it into two sections. The first section is integer system, and the second section is mathematical induction. Okay, and mathematical induction is for theorem concerning integers. Okay, concerning positive integers. Now let's go to section 1.1, integer system. We know that the set of integer is denoted by this z, okay, which is a set containing 0, 1, 2, 3, 4, 5, 6, all the way and so on, and negative numbers, minus 1, minus 2, minus 3, minus 4, minus 5, and so on. In integer system, plus sign and this dot sign satisfy the following axioms. The first one is algebraic properties. The second one is trichotomy law. And the last one is well-ordering principle. We will walk through these three axioms in the following videos. Today, I want to go to algebraic properties of integers. So we start with these axioms, okay, or these properties. We have first 6 properties. The property number 1 or P1 is closure property. Okay, and we have closure property under addition and under multiplications, meaning that if you have any two integer, let's say a plus b is still an integer. Okay, so if you pick these two integer ab, meaning a plus b is an integer. Okay, you might say the axis. Okay, if you pick two integers, you might say their axis integer z such that a plus b equal c. And closure property under multiplication, you gotta have two integer. Any two integer, let's say ab. Okay, a times b must be integer. Okay, this is closure property under multiplication of integer. You may say for any two integers ab, there exists an integer z such that a times b equal to c, like this. Okay, now let's go to the second one. The second property is associative property. The first one is associative under addition. If you have three integers, any three of these integers, and you want to add three integers, you might have to add the first two integers and then add the last one, or you have to add the last two integers and add the first one. The same goes with multiplication. This is associative property under multiplication. If you have three integers and you want to multiply all of these three integers, you might multiply the first two integers and multiply the last one. Or you might have to multiply the last two integers and multiply the first one. Okay? Meaning that you can switch the group of two integers to add to and or to multiply. Alright? The third one is identity properties. So there will be additive identity and multiplicative identity. For additive identity, there exists 0, which is an integer, such that a0 plus a equal to a, or a plus 0 equal to a. It's like 0 is a mirror for a. Okay, when you add 0 by a, you're gonna have just a. And a is any integer. Okay, so this means that 0 add any integer a becomes just a. Okay, so we might say that 0 is the additive identity of integers. And multiplicative identity is that there exists 1, integer 1, such that 1 times a equal a, or a times 1 equal a. It's like number 1 is a mirror for a when a multiply number 1. Okay? A times 1 becomes a. 1 times a becomes a times 1 becomes a for any integer a. Okay, so 1 is the multiplicative identity of integer. Alright, now number 4. Property number 4 is additive inverse. For each integer a, there exists minus a, which is an integer, such that minus a plus a equals 0, or a plus minus a equal to 0. Okay, and what is 0? 0 is multiplicative. 0 is the additive identity of an integer. All right. Property number 5, or P5, commutative property. What is common to commutative property? We need to have two integers, and you can have a plus b equal to b plus a. You can switch the position between these two numbers when it's come to addition. And commutative property for multiplication, if you have two integers a times b becomes b times a. They are the same. When you multiply two integers, you can switch their position. And the last one is P6, distributive property. If you have three integers a, b, c, then a times b plus c becomes a times b plus a times c. Okay, you distribute this a into b and c, and you might multiply the sum of two numbers from behind, and then you're gonna have a times c plus b times z. All right, so now let's go to the next page. So take a look at this note. If we have these three tuples here, z is a set of integer, x is addition, dot is multiplication. These three tuples denote the system of integer. Okay, meaning that the system of integer consists of plus and multiplication. And AB denotes a times b. A minus b denotes a plus minus b. Okay, so from P1 to P6, these properties here we can prove following theorem. So the first one, in the integer system, only 0 is the additive identity. Number 2, in the integer system, only 1 is the multiplicative identity. The third one, for any integer a times 0 equal 0a equal to 0, meaning that 0 times an integer becomes 0. The fourth one, if a, b, c are integers and a plus b equal to a plus c, then b equal to c. It's like a cancellation, right? Addition, cancellation. Okay? Additive cancellation. So, let's go to the first one. Let's prove number 1 here. Okay? Let's prove number 1. So we want to show that only 0 is the additive identity. So what I have to do is to suppose that there exists, let's say x, okay? I may write there exists an additive identity x, okay, such that a plus x equal to a, or x plus a equal to a. What is a? A is any integer. Then I'm gonna try to show that this x becomes 0. Okay? So I want to start with this equation. This equation holds for any integer a. Okay? So since ax equal to a, okay, I gotta say since these equations this one and this one hold for any integer a. What does it mean by this? Does this mean that I can plug in any integer a? Okay, so I want to use plug in a to be 0. Okay, then we're gonna have 0 plus x equal to 0, or a plus 0 equal 0. Now, what can we do next? Go back to properties. Here, I want to use property number 3, which is additive identity. So we know that 0 plus a is a, okay? So by P3, okay, 0 plus a equal to a, right, for any integer a, okay? So we can use a equal to x. Then let's see, okay? So we're gonna have 0 plus x equal x, okay? And then from this one and this one, it will imply that x equal to 0. So since 0 plus x equal to 0, and 0 plus x equals x. Okay, what do we have? We could have x equal 0. This shows that x equal to 0. Now, we can also use this equation to show that x equal to 0. Okay, so again, I gotta use the third property. So we gotta have a plus 0 equal to a. Okay, for any integer a. So what can we use for an integer a? So we can plug in x into this equation. So we can use a equal to x. Then we gotta have x plus 0 equal x. And then since we have this equation, okay, so x plus 0 equals 0 and x plus 0 equal x, what do we have? So we gotta have x equal 0. Alright, so therefore 0 is the only additive identity. Alright, that's a proof of number 1. Now what about number 2? Number 2, okay, number 2, let's prove number 2. For number 2, it's going to be the same as the first one, but we will take a look at the multiplicative identity. So I will suppose that there exists an integer x. Okay, I will suppose that there exists a multiplicative identity. Multiplicative identity x. Okay, such that 1 times x, right? Sorry, x times a equal to a, or a times x equal to a for any integer a. Okay, as we can see, these two equations hold for any integer a. Okay, so these equations hold for any integer a. So what does it mean by this? This means that we can plug in any value of a. In this case, I want to use a equal 1. So what happened next? We gotta have 1 x1 equal 1, or 1x equal 1. Again, we want to use multiplicative identity, which is in P3. So 1 times a equals a times 1. So this is what we have. So we gotta have by P3. P3 So what do we have next? 1 times a equal a, okay, for any integer a, okay. So we can use a equal to x, okay. We can use a equal to x, hence what happened to this equation? So we're going to have 1x equal x. Now we have this one and this one, right? Okay, oh, this one and this one. Okay, so since 1x equal to 1 and 1x equal to x, x becomes 1, okay? X becomes 1. And again, by P3 again, a1 equal a for any integer a. Then what do we have? So we can use a equal to x, right? We plug a equal to x in here. Hence, we're gonna have x1 equal x. Okay. Now since we have x1 equal 1, x1 equal x, what do we have? x1 equal 1 and x1 equal x, we're gonna have x equal to 1. So therefore 1 is the only multiplicative identity. Alright? Okay, now let's go to the third one. Okay, the third one is that for any integer a times 0 equal to 0 and 0 times a equal to 0. Alright, so let's prove this. Okay, and I want to show that a times 0 equal to 0. So I will let a be any integer. Okay, then let's start with a0. As we can see, a0, if we have a0, what do we have? We could have a times 0 plus 0, okay, which is turns out to be a0 plus a0. Okay, now what next? What is just 0? Okay, 0, when this comes to 0, 0 is the difference of the same numbers. So we can have a0 minus a0. But a0 is a0 plus a0. Okay? So we could have a0 plus a0 minus a0. Then, I forget this equal sign. Then it turns out to be a0 plus a0 minus a0. Then what do we have? We can have a0 plus minus a0. This one becomes 0. Okay, so we're gonna have a0 plus 0 equal a0. Okay, 0 is now becomes a 0. Alright, so a0 equal 0. And next one. Show that 0a equal 0. Again, we will let a to be any integer. Okay? Then we're going to have 0a equal 0 plus 0a, right? 0 plus 0 is 0. And we distribute this a into this 0, we're going to have 0a plus 0a. Okay? So we're going to have 0 equal to, again, the same number, 0a minus 0a. So it's become 0a plus 0a minus 0a. Okay? And we use associative property. We're going to have 0a plus 0a minus 0a. Then it's become 0a plus 0a plus minus 0a. Okay, so this one becomes 0. So we're going to have 0a plus 0. So we're going to have 0a. Alright, then 0a become 0. Okay, so we show that we have shown that a0 equal to 0a equal 0. Okay. Okay, great. And the last property, the last one of this theorem, theorem 1.1.1. If you have three numbers or three integers, a plus b equal to a plus c, then b equal to c. Okay, let's prove this. So we let a, b, z to be integer. Okay? And suppose that and assume that a plus b equal to a plus c. Okay? And I want to start with b. So b is, what can we do? B plus 0. And 0 is a plus minus a. Okay? And then what can we do next? We use associative property. So we're going to have b plus a plus minus a. And then commutative property, we're going to have a plus b plus minus a. A plus b is a plus c, okay? It's a plus c. So it's become a plus c plus minus a. And then we use commutative property under addition. A plus c become c plus a. Therefore, we're gonna have to use associativity. We have c plus a plus minus a. So a plus minus a become 0, and c plus 0 is just c. Okay. So hence we have proved that if a, b, c are integers and a plus b equal to a plus c, then b equal to c. So we can cancel a both sides. Okay. So that's it for today. Alright. And in the next video, we're gonna prove this theorem. Alright.